Okay, welcome back. So we have seen the erosion and dilation, as well as the medium filter for morphological operators. Now, these two fundamental erosion and dilation fundamental operators, on top of that, there will be one last fundamental operator. And the other operators that we will see will be a combination, a combined usage of these fundamental operators. And that is the hit and miss operator. So it's hit miss operator that I want to mention. The hit miss operator is unlike the erosion or dilation where there's a single mask. It contains two masks, one mask for the object, one mask for the background. So it's not only the object mask kind of an attitude that we had for erosion and dilation. So B in general consists of an object mask as well as a background mask. And the hit miss operator will be notated by this, like a circular convolution like notation. X operating with a mask set of B is equal to X dilation with the object set difference. That slash is also kind of an operator which I did not mention about, but I can explain it now. It's called the set difference, kind of an XOR operator. As long as they are different, it produces a positive, a one kind of thing. X eroded by the background. It essentially consists of the B can be visualized like this. For instance, we have these three object masks, as well as, let's say, these 5 background mask points marked by red. So it essentially finds in an image if the image has, if X has from the right and from the left containing some pixels like this, and it has this bottom right corner like this. This bottom right corner will be discovered by this hit miss operator, because as you see, it contains these 3 pixels that match to the object and these backgrounds which matches this time to the background as well. So everything matches and it finds that position. It's like the template matching at the boundary of an object. Clearly the hit miss operator works only on the boundaries of the objects. So if you're looking for a spike or something like that that protrudes from the object, you can find it using this hit miss operator, hit miss kind of an operation. Now, these are the fundamental operators of the erosion, dilation, set difference. Let's also mention about that, and hit miss. I didn't mention about the set difference because it's like the intersection kind of an operator. It's so trivial that we don't really need to mention about it. Now, these operators satisfy some properties. These are quite natural properties, but they are mathematically nice, and knowing them and knowing the notations, etc., will help you write manuscripts or solve questions and write out the answers to the questions, etc. So it's more analytical way of looking at it. However, I agree that these morphological operators and the ones that we will see right now are mostly for practical purposes. They are not very much analytical concepts. They are more towards algorithmic way of making an implementation for a purpose. And those purposes I will talk about a little bit later. But now let's look at the analytical properties. The first one is they are shift invariant. Clearly, they are not linear, but they are shift invariant. So the object may be here or here shifted or here, and the outcome of the morphological operators will be shifted according to the position of the object, of course. The second one is X dilation, the union of two masks or two structuring elements is actually equal to X dilation with B union X, start it again, X dilation with B prime. This B prime is not the exclusive set of B or anything, it's just another structuring element. So you may separately dilate with B and B prime and then combine the results for the combined dilation operation. And the extension to this one is X erosion with B union B prime. And that is X erosion B and X erosion B prime in the intersection. This time, of course, it cannot be union, they will have to be intersected. So the smaller shape will be emphasized with this intersection. These are quite logical. I'm sure you will be able to understand these properties. Nevertheless, we're just writing them out. Now, X intersection Z is eroded by B is equal to X eroded by B intersection with X eroded, sorry, Z eroded by B. So let me correct this. Z eroded by B. And the last property we can talk about is what's happening to X erosion B, further erosion B prime, for example. That actually corresponds to X erosion with B dilated by B prime. Because if you erode by B and erode further by B prime, it will become even a smaller object. And it's equivalent to first increasing the mask, the structuring element size so that it erodes more. And then you erode X with that larger one in a single shot. X dilation B, dilation B prime is similarly X dilation with B dilation B prime. So again, you come up with a larger structuring element, a larger mass by B erosion B prime, and then with that larger structuring element, you erode, you dilate X altogether, and it becomes even a larger object. Now, knowing these properties yields some question marks regarding what would happen, for instance, if I first erode and then dilate, or if I first dilate and then erode. We didn't write it in the form of properties or anything because they essentially correspond to some semi-fundamental operators within themselves. And one of them is called opening. So opening is So commonly used that there's a name given to that, and there's a notation given to that. X opening B is X sub B, and it's equal to X first eroded, becomes smaller, and then dilated by B. And so it's a shape size preserving. It's not preserving the shape, of course, but the size is preserved. First, you erode and then dilate. So why are we doing this? What could be a typical application for this one? The typical applications are many, in fact. For example, if you have this kind of an image where, let's say, you can extend the image here. The 3 by 3 left-hand block and 4 by 3 right-hand block are connected with one pixel. There is one single pixel over there in between. But the connection is poor. So if you open, if you apply opening to this, it will be converted to this. Where this very thin connection is totally gone. This helps, for instance, as an application, printed circuit board inspection and such inspection image processing applications to become automatic. For instance, in a PCB, there may be a connection between two legs of a transistor and a resistor, maybe, I don't know. But there is a place like this where this lead path becomes dangerously narrow, but it's still connected. So you want to detect this as a defect candidate, because there is a risk that probably because of the reduced width, the resistance will be increased, the conductance will reduce also. Therefore, it will heat up from that narrow position, and after some use, maybe it will be disconnected. It may become disconnected. So if you apply opening here, it may, if you do it properly with the proper structuring elements, masks, it may be transformed into the right-hand side image, and then using some logical operators, etc., you can immediately understand or realize that this part and this part are now disconnected. So for this kind of a dangerous place detection, the opening mask or the opening algorithm is usually applied. First erosion, then dilation. It will eliminate thin connections. The opposite of the ordering is called closing. And the notation is X superscript B, which is first dilation and then erosion. So again, overall shape size is more or less preserved. But what would happen then? The thing that's gonna happen will be like this. If you have these 3 dots and nothing in between, and then these 3 by 3 dots again, by closing, now it's going to make it like this. So it's going to incorporate these extra pixels. Why would we do that? It may be because we want to see if the distance between two objects are too near or not. If the distance is too small, then they are too near, and that's also another danger. Again, a PCB example application is if there is a PCB path like this. Of course, they are not connected, they are disconnected, but they are too near to one another. And according to some high frequency signals or high voltages, there may be an arc from here to here. There may be a capacitive effect between the two, or they may be considered with a high resistance, but still with a connection, okay, at some frequencies. So it's a dangerous thing. And if you apply closing, it will close up everything and show that they seem to be connected, which is an error, of course, that is easy to detect. So closing is an inspection tool to see whether two objects are too much near to one another or not, because they will be merged using closing. Now, these are the easy ones to understand, and they are very fundamentally utilized in automation systems with imaging. The others are a little bit more difficult to understand in terms of the notations, but algorithm-wise, I will try to explain, and you will be able to find the standard algorithms in MATLAB and in other, like OpenCV and other libraries, image processing libraries. So algorithm is important here. The notation may be a little bit disturbing. For instance, there is a term called skeleton, and the skeletonizing operator notation is indicated as X eroded by R sub B set difference X eroded by R sub B opened by B. So and this is one step of the skeletonizing operator. If you do it iteratively, then the union of R from 0 to R max of these operators, which one of them is the thing that I have described, that is X erosion RB set difference X erosion RB opened by B, where R max is or R is a radius, or it's a disk radius. So it essentially describes a mask, a structuring element, circular kind of shape, and Rmax is the maximum size of, after which X erodes down to an empty set. So you are like peeling with a disk from the edges at various peeling thicknesses. You peel, and you peel from everywhere with a circular symmetric. So it's like shaving, and it becomes so small or so thin that after that you shouldn't continue peeling. So you stop at that position. This union operator is essentially doing that kind of an operation, and you come up with only one or two branched single pixel thick shape, which is like the skeleton inside the shape. So the shape may be like this, I don't know, and the skeleton that will be achieved afterwards will be probably like this, these three lines. All right, and you will be able to find such operators. It may also be obtained in various ways. There are a few algorithmic alternatives to this skeleton operator. One of them is, for example, thinning. And thinning has this notation X, O, B. So you thin with B, which is one step of thinning, like the peeling that I have been describing. And that is the difference, set difference between X and X, this, what was this hit miss operator, if you remember. It's like the circular convolution. That star is the thing that I'm going to use. X hit miss B. This is one step directional hit miss, because B is consisting of typically something like this: 4 pixels from the object and 3 pixels from the background. As you can see, at the right and left, there are 2 don't care pixels. That doesn't need to be considered. But this B is making a direction for the peeling or thinning from the top of the shape. Okay, that peels from the top of the shape. So you rotate now B with some certain amount, 90 degrees maybe, or maybe less. So the rotated version of B may correspond to some different shapes, but with a characteristic that some parts at an angle will correspond to the object and the other parts will correspond to the background. So you rotate B by saying B1, B2, B3, etc. They are rotated versions of B. You're just rotating, and you come back to B again and again. And with that set, you apply thinning with a set of B's, which is essentially like saying XOB, OB1, OB2, operation again, B3. And it goes on like this, doing it again and again with the rotation. It performs the operation so-called thinning. And the thinning and the skeletonizing will make differences at usually the ending points. I'm not so sure about that, but one of them is expected to give from here, for example, some thinning output like this, whereas the skeleton will be a different one. Maybe this. Okay. So thickening is out of context because it's like dilation. Dilation is a thickening operation, so we don't really need that. But once you do skeletonizing and thinning, an important operation which is very difficult for me at least to explain is the pruning. For the native English speakers, they would know what pruning means, but for Turkish people, sometimes you have never heard of this in English language books or anything. Pruning means in Turkish budamak. Okay, so it's essentially cutting the parasitic or extra branches. For instance, these may be eliminated. These 3 branches may be eliminated by pruning. But pruning is an interesting morphological operator, and it runs with complicated algorithms. Therefore, the analytical way of making the representation is a little bit difficult. It starts by 2 definitions of X1 and X2, which is, one of them is thinning. It starts with thinning. Okay. And then X2 is the union of 8 direction-wise hit-miss operators of x1 with rotated bi, which essentially determines endpoints. Because for pruning, the detection of this endpoint is critical. For example, this is an endpoint. Okay, from that endpoint you proceed inwards, and if something else is starting before and reaching to a junction before that, we want to eliminate that branch, and meanwhile this branch will go inside this much at the same length. So one of them is eliminated. The other one, which did not reach to the junction yet, will be kept, and we are going to therefore prune this branch. That's the idea, in short, about pruning. And finally, x pruned is x1 union x2 dilated by rotated version of B, and intersection with X. This is a difficult explanation or notation, and honestly speaking, when I realized it from the book, it also gave me some empty points. I'm not very keen on understanding this kind of notation. And here B, by the way, is notated as 1 1 0 0 0 0. These zeros are the background on pixels, and ones are the foreground on pixels. So B consists of two parts. It has a foreground and a background. But I know what it does, and the best way to to utilize or have a better understanding about these operators is to look at the libraries and to run them for actual shapes. See what it really does for your shape. For example, you can have a black and white, a binary shape of something, of a human, for example. And then you put another shape for a screwdriver. And then you put another shape for a banana and things like that. And you apply this thinning, skeletonizing, and pruning operators at different settings of B and see what kind of things it will produce. You will have to experiment on these things for usefulness. And usefulness of these things are very critical, they're very important. Many of the factories, production facilities, plants are relying on automated manufacturing where image processing is very critical and shapes are very critical. Most of the manufacturing plants are working that way. So if you say that I have seen image processing at graduate level, it's only this level that we can tell you about, but experience is very important, and for the experience you have to exercise, you have to see what could be the outputs of these morphological operators for some certain shapes. Only then you will know how to change a parameter, how to adjust this B mask, for example, for your own purpose. Without it, you will have to experiment a lot of times, and it will take too much time, too long time for the factory to benefit from your image processing. So that's all I would like to talk about. If you have ever seen the actual physical copies of the image processing books, like from Gonzalez, the famous image processing book, which I highly recommend. It's huge. It's a very big book. And there are so many things that we haven't talked about. like topology we didn't talk about. Many of the transforms we didn't see. And there are some dedicated and specific operators for some applications. There are specific applications for those, and they are all very much mentioned here. We have seen some color concepts, but we didn't talk about the color standards yet. We didn't talk about specific or particular standards. We just mentioned about those things, but we know how to make color reproduction, at least theoretically. We haven't seen the fundamental transformations of like Z transform. We didn't design any filters. That's signal processing, digital signal processing, which is very important for image processing too. Two dimensions is a very generic way of designing some filters which will eliminate some information, which will stop some frequency content, and it will pass some other frequency content in two-dimensional frequency space. But we didn't design them. We didn't design any gradient filters. I have just given you a few gradient filters, like the Sobel operator and etc. But they are all design issues. We didn't see any examples of 5x5 median filtering or erosion and dilation. What would change if I increase the structuring element? What would change if I change the shape of the structuring element? For example, a ring-shaped structuring element where inside is empty, the ring is full and outside is also empty. It's not really a convex shape. Right? That would be a very interesting behaving structuring element for opening and closing, maybe, who knows. The only way to know it is to apply and see what's really happening. So the topics are huge. Unfortunately, we don't really have the time, nor we have the initiative for that, because for this course, the fundamental concepts is more critical. We want to really understand what's going on so that you can go deeper into the details of that. That's the only way we could proceed. This is not an undergraduate level image processing. In the undergraduate level image processing, more applications and more getting familiar with OpenCV or MATLAB would be critical. Here, you should be also aware of the mathematical or analytical ideas behind these image processing tools. But it's not PhD level, for example, which is not very much detailed. So I would like to stop at this point, and I wish you good luck for your presentations and projects. I hope that you come up with some interesting and intriguing projects that would be very beneficial for you and for us as well. It's now your turn to come up with an idea and explain us how it's related to image processing and what specifically you're doing and what kind of results you have obtained. So we are eager to seeing those outputs. Now, that concludes my talk, and I am stopping the recording.